Welcome everybody to this webinar. We're still giving any person that is still queuing to enter the webinar a few minutes before we start. So we'll be starting shortly, but stay tuned. So just as a filler, we'll do a bit of background information. So my name is Pierre Josso. I'm the Deputy Director of the Critical Mineral Intelligence Centre at the British Geological Survey. And for this webinar, I am joined by Gavin Mudd, who is the Director of CMIC, and John Paul Horsey, which will be our facilitator for this session. So the webinar, as I said, will start in a few minutes with a presentation on how the assessment was conducted over the last few months or so by the CMIC team. And we will present an overview of the main findings from this iteration of the UK Criticality Assessment. And the rest of the webinar after that will be a Q&A, which will be open to all participants. So please use the Q&A function at the bottom of your screen. We will do our best to answer as many questions you may have during this session. Some of those may be answered in writing, so please keep an eye on these. If some of those questions are a bit, really getting into some details that we may not necessarily be able to answer straight away during the Q&A, we will do our best to take it away with us and send them some answer later down the line. So I think we probably have enough people that have joined. We have currently about 250 people plus that have joined. So it's my pleasure to introduce you, Gavin, for this presentation.
Okay, thank you, Pierre. I'd first of all like to acknowledge the Department for Business and Trade. The funding, I guess, that we receive is from them, and so the program of work for this year, the major project, of course, was a big update on the criticality assessment for the UK. So I'd just like to sort of acknowledge their role and their support throughout this sort of process for most of this year to date. I'd also like to acknowledge Pierre, sort of my deputy, but also the entire CMIC team. We've got a sort of a large team here that has done a lot of work and put in a lot of hard hours in pulling together the data and basically the whole assessment. So let's get started. When we're looking at mining, we're thinking about metals, we're thinking about minerals. We extract different resources from the earth for energy in various ways. And so mining has really changed. We've moved from sort of much smaller scale mining to much sort of larger scales to really meet the demands of growing population, but also the fact that we're using more and more all the time. So not only do we need a wider variety of metals now, if we look back over history, as we can see on the sort of right-hand figure there at the bottom, we also need more and more of them. And so this constant technological evolution is really what's driving a lot of the change we see in our modern world. Whether it's renewable energy, whether it's electric vehicles, whether it's digital technology, without forgetting traditional industries like agriculture and construction and others as well. So a lot of these sectors are obviously pretty important. But we want to make sure we do mining right, and we want to make sure that we've got a responsible sort of supply chain. Otherwise, we might call that a sustainable supply chain as well. So we need these materials, and we need to understand where they come from, and then how we use them, and what to do with them once we've finished, say, using them. That's where a criticality assessment comes in. And a criticality assessment allows us to sort of rank those materials, those minerals, those metals that are at higher risk. Now, when we say risk, there's really two parts we typically look at for a criticality assessment. And so the first one is really the supply disruption. So is there a chance or a risk that the supply of whether it be cobalt or platinum group elements or other elements we're interested in, are they at risk of being disrupted, and therefore we won't have that supply? The next question, or the dimension that we have to think about, is what's that impact? And so how vulnerable are we to an instance of a supply disruption? So if we look at cobalt, for example, in the Congo in Central Africa there, in the late 1970s, there was civil unrest that lasted the best part of 20 years. And so for the aerospace sector, which was one of the major users of cobalt coming from the Congo, they went to substitution. So the higher price basically wasn't tenable for them. So they worked hard and developed substitution as their approach to solving that problem. Rather than just waiting for these problems to occur, a criticality assessment is really a risk assessment. It's basically a process where we can identify those metals, minerals, and potentially energy, etc., that's at risk of a supply disruption, and then trying to understand what's the potential impact of that. So, in other words, how vulnerable would the UK be? Once we've finished that process, we choose a threshold and we say, this is our pain point, so to speak. This is the sort of stuff, the line where above this line, that's really, really important. And so we really concerned about those ones, and they're critical minerals. So they're the ones that we really want to emphasize as probably being the more important to solve relative to others. Now, stuff that's not designated critical doesn't mean we don't use them, and I'll come back to this point. It just means that from a risk assessment point of view, we're looking at critical minerals as those that really require I suppose, more attention, a greater risk of supply disruption or things like that. And so that's the process that we go through in doing a criticality assessment, basically looking at those risks, pulling together all of the data, and then analyzing that. Look at the previous assessment that was done for the UK. It was done about 3 years ago, and it looked at just 26 materials. And they were largely focused around technology and often a lot of decarbonisation, but also digital technologies. And out of that, there was 18 designated as critical minerals. And we can see the results on the right. So on the bottom, we have UK economic vulnerability. On the left-hand side, or the y-axis, we have that global supply risk. And so the quadrant approach, so we have a threshold basically of 1.4 for each dimension. And so that gives rise to that sort of orange quadrant, which is where the critical minerals are derived from. After that, the UK government provided funding to establish the Critical Minerals Intelligence Centre here at the British Geological Survey, and that's managed through the Department of Business and Trade. There was also the Critical Minerals Strategy under the previous government that was launched, a refresh done in March 23, and we're now in the process of developing a new industrial strategy for the UK, and then there'll be, in response to that, there will be a new critical mineral strategy developed as well. So if we look at where we're up to now, in the past couple of years, we've been doing a lot of work. We've done a whole project looking at the whole methodology and the detailed calculations behind criticality assessment. We also wanted to expand the scope. One of the problems, of course, last time is that a whole range of sectors, including some traditional sectors like agriculture or construction, the materials required for those weren't really included. So we wanted to make sure that we capture really the breadth and depth of the UK economy so that we can make sure we understand the material basis for the UK's economic activities. The scope was expanded to 82 candidate materials, and I use materials in a very general sense, and we use minerals or critical minerals for ones that get designated as so. But acknowledging that when we say critical minerals, things like helium, for example, is a gas. We can see here we've got most of the periodic table is sort of laid out here, and we can also see the family of rare earth elements in there as well. Now, I mentioned we take a risk assessment approach, and part of the work that was done, and that was work led by Pierre before I joined CMIC a year ago, but changing the way we look at risk, and certainly within a criticality assessment. If we look at the left-hand side, the box here, we can see that quadrant approach. So we have a threshold for vulnerability, we have a threshold for supply, and you have to be above both of those in order to make sure you are inside that high quadrant. Now, when you're looking at that, in risk management, we often think of a high probability and a low severity risk as we might rank that as a medium risk. But if we have a low probability and high severity risk, that's still a medium risk. So they're about the same. And so when you're looking at that, if we go to the little graph in the middle here, and if we take our value of 4 as our threshold for risk, we can see that there's some ones down the sort of bottom here that are below the threshold, say, for supply risk, but certainly above the threshold for vulnerability, and vice versa on the left-hand axis over here too. and yet the scores are about the same. So from a risk assessment point of view, you've got a 5.2 here, you've got a 5 sort of in the middle there, and then another 5.2 up the top here. So they're really scoring about the same. Now, if we increase the resolution of that and sort of start to calculate it out in a more detailed way, right, remembering that when we're calculating risk, we're taking the square root or the geometric mean of the product of probability and severity. In our case, for criticality assessment, that means vulnerability and supply. We can calculate that risk score or criticality score. And so if we choose a value of 4 as our threshold for distinguishing what we call critical versus important but not critical, we can see we get a curve. And that starts to allow us to really understand the equivalence. So risks that have a high probability or high vulnerability and low supply risk versus those that have maybe a lower vulnerability, but certainly a high supply risk. So part of the work that we've done in the previous financial year was basically a revamp of the methodology. So there's various factors or indicators that we use to calculate the global supply risk. We can see there that we're looking at production concentration. So where in the world does mining and refining occur? Looking at global trade, the net imports by country, the companionality. Some metals like cobalt are a co-product or a byproduct, so you have to mine the copper or the nickel first. But also thinking about recycling, where how much are we actually doing in recycling? Because that can be an important secondary supply. So we put all of that together. We also use some weighting factors, and those weighting factors are chosen based on the quality of the data and where we think the most influence is, and that's helped chosen with our stakeholder engagement. Then we look at economic vulnerability along the bottom, and that's based on apparent consumption, and that's using economic data to look at any UK production plus imports, and then minus any exports, and that's done on a value basis for the UK. We look at net import reliance and we calculate that as a percentage. So to do that, we calculate the difference between imports and exports and apparent consumption calculated on a mass basis. This time we chose to sort of keep the links into the gross value added, which is understanding the economic sectors for different materials get used in. So if we're looking at an element such as rhenium, it gets used in the aerospace sector in jet turbines. So the use of that rhenium is attributed to the gross value added for making jet turbines. And so if we think about our previous assessment, our 2021 assessment, I've just taken some examples from that. We've got germanium, tantalum, tin, and then nickel. And so if we look at that, we can see that using the quadrant, certainly tantalum and tin were designated as critical, but nickel and germanium were not. Now, if we're looking at it from the way that we now view risk as the product of our vulnerability and our supply and the square root of that, we get this line. And so we could say that if we use that line, germanium and nickel would certainly be included as critical minerals, but tin would still be excluded. So if we think about the significance of that, if we chose our value of 4 on our threshold and replotted that, we'd use the yellow line and we'd be able to incorporate all of those, because ultimately when we're looking at, say, nickel versus tantalum versus germanium they're all about the same level of risk. So if they're about the same level of risk, then they should all really be called critical minerals because they're all about the same. All right, and tin, if we choose a threshold of 4, tin would obviously still be in. So we think this is a really important approach and a good sort of step forward, I guess, for the way we approach assessing criticality and then deriving a critical minerals list. Let's look at our results. This is the way our 2024 results look. There's certainly some changes we've made, I guess, to the candidate list. There's some commodities for which there's insufficient data to reliably plot, and we can see that list down the very bottom in the fine print, but there's some stuff that stands out. A lot of the list above our threshold of 4 are very commonly assessed as critical. We have tungsten there as W, we have our rare earth elements, REE, our cobalt, germanium, gallium. We also have zinc there, tin, for example, lithium, but we also have iron. Now, we believe we're the first in the world to actually list iron as a critical mineral. And We think it's actually the right interpretation. And if people are interested, I have the EU plot to show later. But where iron plots in our graph, just to the right there, in terms of very high economic vulnerability and a sort of a modest supply risk, it's clearly above the line. It's clearly therefore critical. So there's a lot of sectors that, of course, the UK uses iron for. It connects into the automotive, the construction, aerospace, and others. So we believe iron is certainly correctly identified. Another sort of result that may be a bit unexpected is palladium, which is literally just outside. Palladium, being a platinum group element, is always associated with platinum, rhodium, ruthenium, and iridium. So we can sort of see these just above platinum up here. All right. So we don't believe that's going to cause any issues in the way that say all platinum group elements will be dealt with. It's a recognition that palladium is more widely supplied and has a lower supply risk effectively. But copper, we can see sort of down the bottom of the graph here, copper is not critical. And that's because it is reasonably well supplied at the moment. And we're looking at the economic value in the way that we use copper, which is in our electricity systems, it's in our electronics, it's in our homes. We certainly have a wide use of copper, but it's not as high a value across the UK economy compared to things such as iron. And so it has a lower economic vulnerability relative to iron. And so it plots well below. And we recognise, and this is in our report, we certainly recognise that there are very legitimate concerns around the ability for the copper sector globally to continue to increase supply to meet things such as net zero. And we certainly go into that into the report, where we look at some of the scenarios and that increase in copper mining that we need to be able to meet our targets such as net zero. Another important example from these results are things like coal and clay, which is right down the bottom left, and that's UK has a very large export industry for that. Previously, of course, up until 2023, the UK used to mine fluorspar. If we look at fluorspar now, that mines stopped and have been closed down and in the process of being rehabilitated. If we change the data at the moment to reflect the fact that the UK would now be 100% net import reliant, fluorine would shift very significantly across to the right and would be above the threshold of 4. It would sit close to a value of 5. And so if that was the case, fluorine shifts. And a reminder, as we see with copper and as we see with other elements as well, criticality is very dynamic. It's constantly changing. And so that's why we always need to keep these sort of assessments updated and moving forward. So let's look at our results on a periodic table. And again, this is our spread, so we can see all the rare earth elements along the sort of the bottom here. All right. We can also see a lot of the iron-related elements, such as manganese and nickel, vanadium. We see our 4 platinum group elements there in the middle and a range of others that are there. And so for sodium, it's not salt. We don't want any confusion about that. The sodium there is listed, which is sodium compounds. And by that, we mean sodium carbonate, sodium nitrate, and sodium metal, which is a minor part of that sort of trade code. So it's sodium compounds there. And for magnesium, we mean both magnesium metal as well as the industrial mineral magnesite. So for the carbon there, we're looking at natural graphite as the material that we've listed as critical. So that's our list. It's 34 in total, and we think it's a pretty well justified list. If we compare the way our new list for the UK, and this is a UK assessment. We're not the EU, we're not Australia, we're not Canada, we're not other countries around the world. This is specific to the UK, so there should be some differences. And given the commonality and the main technologies that we're all using, of course, there should be some overlap as well. And we can see with the European Union on the bottom left here, there is a lot of overlap. So it's the rare earth elements, it's cobalt, a lot of the different alloy elements, the platinum group elements, and so on. If we compare to Australia, we can see, again, a lot of the same elements and the same materials being listed. One of the key factors there for the European Union is that nickel and copper, just like our results for copper at least, didn't meet the criteria for critical, but the EU has decided to add that to their strategic minerals list under their Critical Raw Materials Act. For Australia, they recognise that copper, zinc, aluminium, phosphorus, and tin also didn't meet the criteria that they used for designating critical minerals, and so they've established those as their own strategic minerals list. And that's an important point, I suppose, that in difference, we haven't recommended that here. If we compare the UK list on the top to the two main lists or ways that the US looks at things, on the left-hand side, we see the US Geological Survey, which is a national assessment. And so that's comprehensive like the UK. And again, mostly the same, but some differences there. If we look at the US Department of Energy, it's looking at just energy technologies only. And it does list electrical grade steel, so a specific alloy designed for use in energy technologies. So not iron in total. But again, their list is much smaller because they're only looking at the materials required for energy technologies. If we look at the way that our results might appear if we're looking at different technologies. So across the top here, we've taken our plot and picked out different components in digital technologies and looked at the things, whether it's the sort of the batteries, whether it's the actual electronics and the chips, or the color screens. And we can see a lot of the materials sit above the threshold, but some actually still sit below. So they're still important. If we look at wind turbines or solar panels and also aerospace or jet turbines, for example, we can see that many elements sit above the line, but there's still a lot of other elements sitting below. And so they're still important. They will require a different policy response, I guess. So it's not that we're saying, say, copper isn't important, it's just that it's not critical. So out of all of that, we believe our assessment certainly is the most comprehensive of the UK to date. We've looked at 82 raw materials. We've gone through in great detail. We've looked at using a revised methodology, and we believe using a curve, using this sort of equivalence approach from a risk management sort of approach, really allows better justification of our critical minerals. So that way we really do get a more equal sort of footing to be able to decide what is critical and what isn't. Out of that, we've used a threshold of 4, and we get to 34 critical minerals. And so iron is included, but we don't include copper and palladium, for example. We believe the rest should still be maintained on a watch list. And as we've seen, like fluorine or fluorspar, things can change pretty quickly, not only within the UK context, but also in a global context. So that's important. So there's some of the key sort of findings. Areas for recommendations, we think there's a lot of work that we can do. And this links to, I guess, the sort of industrial strategy that's looking to be developed at the moment in the UK, but looking at the midstream and looking at the material flow. So really understanding not just the primary raw materials, but understanding materials as they flow through the economy in whole. We also think we need to look at better methods that we can understand the impacts of trade barriers, but also trade relationships. It's something that we started to look at, and we felt that wasn't appropriate to be able to include it in this assessment. We think there's a role to say there's a need for deep dive studies, so we can do some detailed global studies on say, copper, some detailed studies on iron in the UK, and really looking at the material flows and understanding the potential for recycling the different alloys. We want to make sure that we maintain those properties of the different alloys for which iron is used. Things like tantalum, critical for our electronics sector, but also tungsten, where the UK, and maybe lithium as well, we could add there, where the UK has some prospective mining potential in the near future. But also looking at different technologies that are on the rise, whether that be energy storage batteries, but especially the information and computing technology, ICT as it's often called. And so the rise of quantum computing, we think, could present some pretty important challenges in terms of material needs and things like that. Where we believe there is future potential for UK domestic production, there's a lot more work that needs to be done to set up the pre-competitive data for that. And that's things like geophysical surveys and so on. Given some of the global sort of geopolitical context and the sort of landscape, we think there's also a need to be able to develop some methods that allow us to do a rapid response. So if there's a particular issue, there's a supply chain disruption of some sort, such as we've seen with Hurricane Helene that recently went through North Carolina and basically caused severe impacts on a high purity silica mine, which is used for making silicon chips. what's the response? What's the sort of impact of that? So we need some to improve our capacity to do that. But also we need to make sure that given everything is dynamic and given some of the changes that we're seeing globally, we need to make sure we keep this effort going so we can make sure we support our industries and move forward and keep the UK in a good productive state. Finally, just like to point people to the fact we'll be having our second annual CMIC conference early next year, and that will be held here at Keyworth in Nottingham on the 26th of February. So if you'd like to, go to our website and you could certainly sign up for our either our newsletter or information or send us an inquiry and we'd be happy to respond. All right, and we hopefully we might see you here in Keyworth. But just finish with some acknowledgements. I would just like to acknowledge the sort of the funding that we do receive from through the Department of for Business and Trade. Without that, we wouldn't be able to do the sort of work and support the UK government. I'd also like to acknowledge the whole team here. It's a very large team, and we've worked hard for many months this year to get to the point of having the project finished now and launch like we are doing. I'd also like to acknowledge the various stakeholders we've engaged with and the consultation processes and all the written submissions we've had. Certainly helped us to basically build that content into the report and make sure that the report really speaks to what's critical, what's important, and various pathways forward. Thank you. Now, I think we're happy to move to the Q&A session. So, JP.
Brilliant. Listen, thank you very much, Gavin, for that great introduction and overview of this criticality assessment that launched today. And thank you to the 290, almost 300 that have taken the time to join us live for this presentation. It's greatly appreciated. Without further ado, we'll dive straight into the Q&A. There's lots of great questions already come in. Still plenty of time to get your questions in. And as Pierre said at the start, if we don't have time to answer them live, we'll do our very best to follow up with written responses to your questions. I think it's only fair that we start off by asking Pierre the first question and give yourself a chance to catch your breath, Gavin. So Pierre, what proportion of our critical minerals use could be satisfied through more or better recycling, i.e. of consumer electronics, car batteries?
Well, I think everybody would love to have an exact number. And effectively, there is definitely an enormous amount of raw material, critical minerals, metals, whichever substance you consider, that we could valorize if we improve the collection, the recovery of those materials. Being able to explicitly define a volume at the end of the day for each of those is very difficult. We have all our data for each of those materials, which is detailed in the annexes if you want to have a look at specific commodities. But effectively, putting in place an improved circular economy is definitely a way of reducing supply risk by having a better collection and keeping resources domestically. That also entails the fact that we would put in place the recycling system in the UK as well, not to export those waste abroad and effectively lose control of this resource. I hope that answers part of the question.
Yeah, another comment I'd add in there as well is it entirely depends on the material you're looking at, but for a lot of them, we don't have enough in our urban systems yet to really feed the flows for recycling anyway. So we're looking at electric vehicle batteries. We're moving from the old lead acid batteries in combustion vehicles to lithium-based batteries in electric vehicles. And so it'll be some years before we've got the electric vehicle fleet and the batteries, within that become available for recycling. So, which is fine. That gives us time to look at the recycling policies, any regulatory requirements, any R&D. So we've got time to sort of build towards that circular economy and improving the way that recycling can help us achieve that.
Great, thank you both. Next question, did you consider the import and export of minerals containing products, e.g. electric vehicle batteries, when calculating the criticality?
That's always a good question. Our assessment is very much a raw material assessment. We haven't gone through and tried to estimate the amount of materials that sit in products, for example. So if you've got an importation of an electric vehicle, that vehicle would contain copper, it would contain lithium, it would contain lots of different steels, and a whole range of other things. And especially given the increasing amount of electronics in vehicles as well, there's that side to consider. So, and if we were to do that, I mean, yeah, conceptually, yes, it's theoretically possible, but that would be an extraordinarily large project to be able to undertake. And especially if you're looking at 82 commodities, and then you're thinking about all the different products that and different materials, components, semi-manufactured goods, etc., coming in and out of the UK, that would be an extraordinarily large project. So our focus, in line with the way that these assessments are done in the EU, in the US, and Japan and elsewhere, is really focused on the raw materials, and that's the sort of the underpinning basis of a criticality assessment.
And I would add to this effectively because there were a few other questions in the chat that kind of highlighted this phenomenon. And effectively, we also heat the resolution of the data that is available to conduct those type of exercise, whereby it is impossible to get clear pictures of the metal content, which might be incorporated within such a diversity of different technology product, chemical product, and so on. And effectively, disentangling trade data on this level would be an absolute fate to conduct in a very, very large project. It's not to say that we haven't done such analysis, but we are doing similar exercise more when they are technology focused, and we're doing a top to bottom approach whereby we are investigating the chemical composition of all the components and at the manufacturing stage from the end product through to the mining sector. And those are much more detailed into some other reports in the foresight studies, which are going to be released fairly soon.
Great, thank you both. The next question is about silicon, and that is simply, does that include silicon dioxide?
Effectively, when we say silicon, we're really talking about silicon metal, right? And then if you're looking at some of I suppose the important forms of that, you really need polysilicon, especially for chips. So when we say silicon, we mainly mean silicon metal, and we separate that out from silica, which is industrial sand.
The next question is about copper. So it's quite a long one, so bear with me. The question reads, copper is not on the list since future supply is a concern rather than current supply. But isn't this one of the key reasons of this list to help promote investment in minerals like copper to prevent supply shortages in the future? Given the average project takes 8 or 9 years to build, then shouldn't there be a time component within the model to account for this?
It's a great question. When we're doing criticality assessment, we're using the last 5 years of data. Now, we do that because that's available and it's reliable. If we're looking at trying to, I suppose, undertake a future assessment, we'd have to both look at the demand side as well as then the supply side. Now, there's a lot of uncertainty in how you build models around that. I've done such things in the past on both sides. So it's certainly possible, but it's not the way the criticality assessments are normally done. We look at where we're positioned now. We think about some of the different sort of supply risks, and we can see that whether we're looking at the platinum group elements, 40% of world palladium, for example, is actually coming from Russia, and that's not subject to sanctions either. So I think there's different commodities will face different risks, both supply risks, different demand risks. And so I think that's always important to be able to sort of account for. So when we've looked at all of this, and we spent a lot of time in the current assessment trying to work out how we could think about including a future derived factor from our foresight studies. So our foresight studies have looked across mainly decarbonisation technologies such as solar panels, wind turbines, electric vehicle batteries, and traction motors, and others. And then looked at what that future growth would be in the UK out to say 2050 to meet net zero, and then what would be the material demand for that. Now, that leads us to around about 26 minerals or materials that incorporated into all of those technologies, but it means we're not doing that for the other 56. So if we were starting to try and incorporate future demand or future supply into the way we do criticality assessment, we'd have to then also do the same exercise for the other 56. And we don't have that. And I don't know any group around the world that does. There are certainly examples individually of whether it's vanadium, for example, and vanadium is not part of our foresight studies, but vanadium is expected to grow, quite rapidly in the near future in response to the use of vanadium redox flow batteries. So at the moment, we felt that if we tried to incorporate a future component into the way we're calculating criticality, we'd be potentially introducing more uncertainty and than you would actually add value. And so for the moment, we've looked at the potential different scenarios. So if we look at lithium's going to increase somewhere between 10 and 20-fold over, by 2050 globally to meet the demands for net zero. So there's a very, very big demand factor there for lithium. Copper, we need to increase, certainly by about 2040, by about 12% over our current trajectory of where we're at with copper. And so by the time we get to 2050, we're sitting at about 2% above current sort of projections. So that I think is reasonable. I think given the challenges there and the uncertainties, and if we think about, when I say uncertainty, if we go back 5 years ago, everyone was expecting a huge increase in demand for cobalt, and we haven't seen that because lithium iron phosphate batteries have come in, and they're providing just over 40% now of EV batteries. So I think there's, these technology changes are, trying to predict them into the future. It's inherently uncertain and very, very difficult. So I think that's sort of why we've chosen sort of to look at some specific materials like lithium, rare earths, and copper in the report and analyze those just on a case-by-case basis. So, I certainly understand the question and the concerns, but I guess from a criticality assessment point of view, our methodology is based on the last 5 years, using that data that's out there and saying where are we currently at and thinking about what that means for the future. So hopefully that helps.
Great. And you mentioned lithium iron phosphate. It's almost like you knew what the next question that was coming up was going to be. So this question,
that's okay.
For batteries, given the rise of lithium iron phosphate as a cathode, should Fe not be highlighted as well on the battery material critical list, and the same for phosphorus?
Possibly, but at the moment, the sort of the growth of lithium iron phosphate batteries is really only in the last 2 or 3 years, maybe 3 or 4 years really. So it's only just starting to appear at the end of our 5-year period. Now that may change in the future, and it's a really good question in a way. And so, but if we're looking at phosphorus, I mean phosphorus is still critical, but the vast majority of phosphorus is used in agriculture. So fertilizer is the sort of predominant use there. So maybe lithium iron phosphate batteries will start to take up a sort of a higher fraction of that. But so there's other technologies, I guess, that may emerge in the near future and continue to sort of change the way that we use different commodities, definitely.
Next question for yourself, Pierre. Is there a list somewhere where the attendees can access quantities and costs of imported critical minerals?
Well, obviously the list of critical raw material changes every time we do a new assessment, but effectively the imported quantities can be tracked using BGS datasets of world mineral productions, and also following some of the trade codes data that we are using into our assessment, which are detailed in the methodology. People can go on to TradeCom data, ProdCom data, and try to track what their specific commodity they are interested into, how much of it is imported or exported by various people. Effectively, at the moment, there is this desire from higher instances, policy from the global nation interested in critical raw mineral policy, to kind of create this global visualization of materials where there are imported stocks and flow, how they're moving. But for some of the reasons we've highlighted before, in the fact that a lot of those raw material effectively are not moving around necessarily in their raw form, but into more transformed product, it is an extremely difficult task to create this harmonized system across different countries. But effectively, lots of data sets which are publicly available can be consulted to track import and export of critical raw material in the UK and elsewhere.
Just a quick point I'd add there as well is when you look at the different supply disruptions across different materials, the links to price is not always obvious. If you look at cobalt, the issues in the Congo from the late 70s caused a huge increase in price. rare earths being exported from China in 2010, when there were really strong restrictions put in place, sent a huge increase in rare earth prices. In 2012, with the civil unrest in South Africa, with the Matakana incident, there was no impact on price for platinum group elements at all. So predicting the link between a supply disruption and price is not easy, and yeah, so I think there's certainly data sources out there for various things, but it's putting it into models and assessments for the future. That's always really difficult.
Great, thank you both. The next question asks, do you have any evidence that UK organisations are adapting, whether that be designs, manufacturing, stock holdings, etc., in response to evaluations like this?
Yeah, definitely. I think what we're seeing is certainly opportunities, whether it be the lithium landscape, whether we're looking at groups, whether it be the platinum group sector, aerospace sector. There's certainly different examples of organizations that are definitely looking at the assessments we do, the lists we provide, and then proceeding accordingly. Because as much as sometimes these are challenges, they're also opportunities. So, and I think that's sort of an important point to make.
Thank you, Gavin. Next one for yourself, Pierre. Have uncertainty bounds been considered within the criticality assessment? Are there any minerals close to the threshold which would be considered critical if uncertainty bounds are included?
Well, a sensitivity analysis, which is what's being called for here, is something we could do effectively, and that could incorporate a lot of different metrics. Effectively, we could assess the quality and the certainty we have into the data itself that we're using and the way this is combined. That needs to be compared across the panel of all the candidate materials and propagated throughout. So this is quite a complex exercise. We are hoping to be able to do some background calculation and check on this, but effectively some of this sensitivity has been minimized in terms of the confidence we have in the data through the weightings that have been put in place for each indicator. But effectively, some of the indicators which are plotting very close to the threshold are very important as well. And this is something which we've talked about quite a lot with our stakeholders, is that criticality assessment, the plotting of it. Effectively, it's a gradient. All the elements, all the materials that we're evaluating, they all are important in one stage or another in some of the products that we use throughout our industry, throughout our lives. But for the sake of policy development, investment, R&D, and so on, there is a necessity to put a threshold, to put a boundary somewhere between those two, and to put a clear list of what's critical, what will be the focus of the government and other industries in the near future. It's also important to remind people that this is an assessment that has been done at the scale and from the perspective of the whole of the UK, for the manufacturing sector at least. And effectively, it doesn't mean that some of the materials which are plotting below the threshold may not be critical for a specific company or a specific industry. And as we've seen with the US, the Department of Energy have conducted their own assessment and are highlighting different elements because they are critical to them. This is an assessment conducted at the scale of the whole economy of the UK, and therefore each company, each person, individual is encouraged really to have a deep down look at their own supply chain on the material they rely on to better tailor their response to such a drive.
Great, thank you, Pierre. Okay, next question. What is the difference between your proposed vulnerability axis if compared to the EU approach of considering economic importance?
Yeah, I'll let you take lead.
It's semantic, really. It's very much the same thing. It's a compilation of similar indicators, really, that evaluate economy, the importance of an element within the economy, whether you consider that has the economic importance or effectively the vulnerability of the economy, would there be a disruption, is roughly the same thing. It's just two sides of the same coin.
Thanks, Pierre. Gavin, next question for yourself. Regarding better assessment of trade barriers, have you thought about how this may affect continuity of the method and comparability through time? Separately, will you look forward to implications of likely changes to trade barriers?
Yeah, that's a great question, because one of the things I guess we always struggle with in looking at criticality is not only is the landscape very dynamic, but we do try and evolve the methodology, so keeping some sort of consistency there. So we would hope that in future we would keep the same 3 at the moment and add, say, a 4th indicator for trade barriers there. There's certainly some ways of doing that. You can look at the frequency of different trade barriers, or you can look at the severity of them. You could look at, do we have trade agreements in place as well? So the positive side. And that's something often that a lot of the processes haven't taken into account. So I think that there's certainly possible ways to do that. But one of the issues, I guess, that certainly we sort of struggled to work our way through was, how do you make this a predictive tool? How do you make sure we're incorporating trade barriers in a way that actually speaks to that level of supply disruption or that risk? And so it's a difficult thing. We haven't, so that's why we haven't used it this time. So I would hope in future it would just be 4th. So you could easily go through and say, here's the initial 3 indicators from this assessment, and in the next assessment, if you've got a 4th indicator, you would add for trade barriers. So I think that would be a way I think we can start to get some continuity there in the methodology, and then looking at what the results mean and so on as well.
Great, thanks, Gavin. Pierre, could you explain how supply chain is taken into account? Tungsten, for example, is used in nearly all cutting tools, but when those are imported into the UK, it's not tungsten which has been imported, it's cutting tools, for example. The example is tungsten here, specific, but it's not limited just to tungsten.
Effectively, so some of the form of those material, effectively, most of the import or export is not as a raw material, as we said before, but in a transformed product. For the case of tungsten, effectively, some of our trade codes that we are tracking within the economic indicator for the UK economic vulnerability track the import and export of cutting tools or machineries, and then we apply a ponderation which consider the amount of tungsten which might be contained within the products that are being exported and imported. And this is where some of the uncertainty effectively arise, given we might be tracking between 3 to 4 codes for some minor commodity, but up to 50 or more for some more important commodity like iron and all the different types of steel. So effectively, if we were to consider a slightly different example, all the different elements, alloying elements, which are incorporated in different type of steel, sometimes we know there's only a handful of % in them, sometimes it can go up to 5-6%. So we can't incorporate within the traded form of manufactured components. If we can evaluate them with certainty, we incorporate those mass flow into the balance of import and export. We could go on for each commodity, but it is effectively a very, very difficult process, and we've gone through for each commodity a long review of which code, which traded form we were confident in being able to evaluate the amount of tungsten, lithium, or any form or any material that we were considering for that specific assessment. And we were trying to start from obviously the bottom with all the raw ores and concentrate, different minerals form, different chemical compound, and then you go into more transformed products. And when you're importing and exporting cars, well, this is where this becomes very complicated, for instance, because of the demultiplication of composition, average, size, group, make, and so on and so on. So that applies across all the things.
Thanks, Pierre. A really good question. Gavin, I've got a nice easy one for you. Mike asks, will the slides be shared following the meeting?
Yeah, we're happy to make the slides available. I think just drop us an email either through the inquire at our website, our inquiries, or things like that. But yeah, happy to do that.
And then Diana asks, well, first of all, Diana starts by saying thank you very much for this presentation. Thank you, Diana, for joining us. The question is, what potential limitations exist in the methodology that you use to determine the current list of critical minerals for the UK?
Probably a range of limitations. Firstly, we are reliant on the data, and we've gone through a lot of trade data, and you can certainly find examples where there's some errors in trade data. So we have to use our own judgment either to exclude such data, to correct it. on what basis do we then correct it? And we've certainly seen some examples there where we feel we can justify corrections based on some different sources. So there's certainly uncertainty there. And sometimes trade codes change over time too. And sometimes you've got issues where one trade code may have 5 or 7 elements actually listed within that trade code. And things like germanium and vanadium and niobium don't normally occur together geologically. So the way they're mined and they're sourced in terms of mining and refining is very, very different. So the trade codes don't really speak to that very well. So then you've got to unpack all of that. So there's certainly uncertainty on those sorts of fronts. For mining and refining data, we're pretty confident on that, where BGS has been certainly a world leader in tracking mining and refining for well over a century. So we've got one of the few groups globally that does do that. So that's where some of the main uncertainties are. And then the other uncertainties, well, what threshold do we choose? And that's a choice. The weighting factors, we think we've got a good basis on our weighting factors for both the supply risk and vulnerability. But that's also where there's some uncertainty. And you could look at trying different weighting factors and see how things may plot differently. We didn't feel that was useful or adds value in terms of this process here. But if we chose a threshold of let's say 6 on our graph, we'd get a very different list of critical minerals. It'd obviously be a lot shorter. If we chose 3, obviously it'd be much bigger. All right, so that choice of where we put the threshold in the end is still, there's some uncertainty there as well. We think we've got that threshold right. We think it's a good choice there to sort of and make sense based on the technologies that we see and the different demands and links across to the various UK sectors. So that's certainly where most of the uncertainty is.
Thanks, Gavin. We've had a couple of questions in about recycling, so I'm going to combine them together if that's okay. Whilst the weighting downplays the use of recycling, this currently doesn't factor in, sorry, let me start again. Whilst the weighting downplays the use of recycling, this currently doesn't factor in recycling yield. How do you intend to improve the recycling data to give a more representative picture of recycling streams? And the similar question was asking about how you plan to incorporate more recycling data in future assessments.
It's a great question. And one of the challenges that you need to think about how you calculate recycling and how you actually quantitatively estimate recycling. If we take an aluminium can, we throw it away, it gets collected, and then that gets sent off to recycling. So the proportion of aluminium cans that are collected and sent off is the traditional way we often think about recycling. Now, if we were to buy a new aluminium can, how much of that aluminium is actually recycled content? And so that's the input recycled content, or recycling input rate, as it might be called. Now, you then have to think about aluminium is used not only in cans, it's used in alloys, in the aerospace sector, in the automotive sector, and other things as well. So then you've got to work out what are all of those types of rates across all of those different end uses. And when you're looking at at recycling data globally, no one has perfect data calculating both collection rates, recycled input rates. In some sectors, there's what we call closed loop recycling that often isn't accounted for by either a collection rate estimate or a recycled input rate estimate. And that's where companies internally within a manufacturing system may actually recycle a lot of material. So you get scrap left over from the production process, and that's fed back into the start of the manufacturing process. Doesn't even make it into, say, a particular product. So there's a lot of complexity, I guess, in recycling, and actually both the data that's out there for things like recycled input rate or the collection rate. There's no consistency around a lot of that globally either. And that's largely because nowhere, I think, it has great data that actually properly maps and tracks all of this across all commodities. So ideally, we'd want the same level of data quality across all commodities. And so we have the same level of sector use data. We have the same level of quality around recycled input rates, collection rates, and so on. And that's something that it's broadly recognized. It was also recommended recently by the Royal Academy of Engineering sort of report that said we need to have a dedicated materials observatory that allows us to build the data set. So we're really calculating these things and understanding not only just the amount of stocks that exist in our systems, but what are the actual recycling rates so we can then plan for that. Because recycling, it can be a much more important source of a lot of different materials into the future. And certainly the IEA, the International Energy Agency, recently released a report looking at recycling of critical minerals. And for copper, we can help reduce that stress on mine supply by improving the way we recycle copper. And that's possible. What we need to look at is some of the technology issues there. Is it consumer behavior? Are there price points we need to think about? Are there regulatory barriers or incentives that we can look at? All of those types of things we need to really think about when we're talking about recycling. And so it's a very difficult sort of area, but we know we need to make a lot more progress in that. And that's certainly an important way that we can help achieve not only greater circularity, but also better security of supply for things like a lot of our critical minerals and other important minerals as well.
Great, thank you very much, Gavin. So next question is for Pierre. Does the criticality assessment take into account materials availability from UK's friends, such as Australia and Canada, thus modifying the criticality rating?
Right, so it's a good question. It's also fairly subtle in the sense that it depends who you ask, who are the UK's friends and how rapidly some of those friends might be changing. There's no judgment about Australia, Canada, or any of the current ones, but it is quite a sensitive topic effectively to integrate. The way we've gone about it, nonetheless, was to incorporate variables on environmental responsibility, sustainability, and governance indicate in our indicators. So effectively, we compiled a range of close to 50 plus indicators that capture those. I think Gavin might have a slide or moving somewhere. Yeah, effectively, thank you. On the production concentration, the share of production from each country is weighted by what we call a compound ESG score, which captured to some extent some of the value that the UK is championing and how it's reflected in other centers of production. So effectively, this can be translated in the fact that even if the production concentration is high, if it comes from a country with a good ESG rating, the risk will be ponderated slightly lower than for a similar level of production concentration coming from a country which has slightly lower standard. So this is the way we've incorporated this dimension. But effectively, this also joins back to the question of trade barriers, whereby we think mostly quite commonly about China putting export ban or trade barriers to some of the raw materials they're processing or refining. But it's important to consider that those trade barriers come from both sides. Most of the time, China is also putting those trade barriers in response to export control from the US, from the Netherlands, from China to their microchip industry, for instance. And the EU Critical Raw Material Act is also a trade barriers. The US Inflation Reduction Act is a trade barrier. So do we consider those are from friendly countries, or are those effectively additional trade barriers? This is quite a difficult topic to simplify into a metrics which would be on a set scale of 1 to 10. This is too subtle to be incorporated that way.
And I think I'd add, we felt that if we tried, it would introduce a lot more uncertainty and arguably more subjectivity as well. And so that's why we felt it's best to sort of keep it focused on a lot of these sort of indicators we can see in front of us here, because that's where there is specific data that we believe is of reasonable quality or very high quality. And so that way it keeps our whole process much more impartial and objective. And then policy can then respond to those types of issues as policy should.
Thank you both. So the next question is asking about sodium, and it reads, sodium is quite a surprise on this list, and you note it is sodium metal / sodium carbonate that is the risk. Given raw materials are available for this, is it just processing that's the limit? How does this compare to something like titanium, which we cannot mine and refine in the UK, and a significant part of supply has historically come from Russia?
It's a good question. When you're looking at, let's sort of flip forward. If we're looking at where sodium plots, so we can see, let me just find it here for a second. Where have we got sodium? Sodium compounds down the bottom here. All right. So it's certainly, in terms of economic value, I guess there's trade codes for the volumes of things like sodium carbonate that are imported. There's also sodium nitrate that's used in fertilizers, so that links to agriculture, and sodium metal that's linked to some chemical uses and so on. So when you're looking at that, that's where the trade data, we're 100% reliant on importing those specific forms. Now, when you're looking at titanium, it's also used in things like ferrotitanium and so on. And again, we're looking at the sectors, but there's less sectors where we're using iron. So I guess the GVA is probably playing a factor there. So, but they're not too different. If you're looking at the overall risk criticality score for sodium, you're looking at about 4.3, where titanium, you're looking at about 5.1 there or so. Or sorry, 4.7. So not too far apart, really, in terms of their overall sort of criticality score. And that's really what we're looking at, is we're not trying to be sort of too absolute in a way about these. This is much more of a relative assessment. But certainly when we're looking at specific sodium compounds, there's a lot of material that comes into the UK, and that's what the trade data shows. The uses of that then link across, whether it's through GVA, into those various sectors. So that's sort of why sodium plots where it does. And effectively, that's the same type of argument we see with iron and others. And so getting that equivalence there, we think, is really, really important as a way to make sure we understand, what's critical versus important but not critical.
Thanks, Gavin. I'm just going to do a quick reminder. We're now past the halfway point in the Q&A. There's lots and lots of great questions still flooding in. In fact, we've got almost 60 still to be answered, which is fantastic. It's great to see so much engagement, and we will do our best to answer these offline, the ones we can't get to. So please do keep entering them in the chat. The next question for yourself, Pierre. During the presentation, it was mentioned that quantum computing might be a future industry that will need to be taken into account. Will this expand the number of materials that need to be assessed, for example, rubidium?
Clearly, yes. Quantum computing, as much as the development of all the future information communication technology, development of AI, is going to put massive strain on a range of very, very minor elements that are going to be essential for the development of these technologies, the use in microchips, the development of the data centers, which are really underpinning the development of the processing power of these new technologies. So effectively, what we're recommending is to do a deep dive on these technologies and investigate where those materials are currently known to occur, where they are being produced, where are the centers of production in terms of the manufacturing sectors, where are all the microchips being produced, where is all the high purity silicon coming from, gallium, germanium, and so on. So there is a very large picture that needs to be gathered, and this is very similar to some of the foresights we're conducting at the moment, and some of them are to be published very soon. So yes, this is something we would really like to be doing. Rubidium effectively will need to be investigated in its own right.
Some other comments I'd add there as well, and it's one of the challenges we have. If we think of iron, there's something like 3,500 alloys of iron. Now we're looking at the totality of all of that. When you're looking at quantum computing, you're not just looking at different materials like high purity silicon, but you're also looking at isotopically pure materials. And that's a type of depth, I guess, in looking at the material inputs that is extremely rarely done. In fact, I don't think I know of an example of a criticality assessment that has actually included isotopic purity. And so that's, we could look at specific forms. The US DOE obviously lists electrical grade steel specifically for energy technology. So there's certain examples where certain materials do get looked at. But again, we need to look at that, I guess, in some ways that would, as Pierre sort of said as well, it's a different approach. You would look at that more as a deep dive into the technology, and then look at all the whether it's high purity materials or the isotopic purity of the materials. So there's some other questions around things like quantum that no one's really started looking at yet. So that's why we're really keen to do that in the near future, because we think it'll be a great opportunity for the UK to make sure we're at the forefront of what's happening with quantum, but also to make sure we really understand what the material basis of it is.
Thanks, Gavin. Okay, we've got another couple of questions that are related, and this time it's in regards to next steps and the role of the government, or how this will interface with the government's plans. So the question asks, what happens now with this assessment? Does it mean that this is now the UK's critical mineral list? And when and what does this mean for the UK government's actions in these areas? The follow-on question, which is related, goes on: how does the UK government engage with specific countries about diplomatic partnerships related to this assessment? And how do we ensure that imports and critical minerals, and which critical minerals we kind of focus on? What was the government's process of identifying state partners?
I think policy is obviously that's the role of DBT, and we have various other arms of the UK government that I suppose develop policy and then implement policy. That policy is informed by our analysis and what we've identified as critical minerals. I guess the next steps for the UK government would be actually the critical mineral strategy, so a new strategy that takes into account our criticality assessment. But we know from the work that's been going on, there is a lot of work going into different trade relationships, looking at different countries and what does the UK need, what can other countries provide. So there is certainly a lot of work going into all of that. And that's where, whether it's DBT, whether it's the Foreign and Commonwealth Development Office, and all the other parts across the UK government that are involved with all of that. And so, and that's something we're looking forward to contributing to. One of the things, I guess, that we're certainly we do is actually international collaboration. And so that's something that BGS more broadly has been doing for a very long time. My home country of Australia, of course, the geological surveys were set up by the British Geological Survey back nearly 2 centuries ago. So a lot of that international work is something that has been bread and butter, not only just from the Geological Survey point of view, but also, I suppose, international trade and so on as well. So I guess that's some of the next steps. But we're certainly looking forward to a lot of that international collaboration, because that certainly is what's needed, because there's some metals and minerals as much as there's prospectivity in the UK for some things and prospects for things like lithium and tungsten to be produced in the UK. We'll still need our international trade partners to make sure we're supplying a whole range of other critical minerals and other important minerals as well.
Thank you, Gavin. Okay, Pierre, next one for yourself. Over time, would it be reasonable to expect that the criticality score of certain critical minerals could be reduced due to interventions by government and related agencies, including financing, regulatory changes, and innovation?
Well, effectively, this is the ultimate goal to some extent. The criticality assessment really is a risk assessment. We know we identify a list of materials which are at high risk of supply disruption and would have a high impact on the economy of the UK. The goal of that assessment is to flag really this material to the government, but also to all the different industries that make use of those materials, and for them to take actions into looking into their supply chain or how to reduce the risk associated with supply, or potentially try to diversify. That can take many, many different aspects. That can be improving domestic production. So this is the case. We have a lot of support from government in doing so at the moment with lithium, tungsten, and other commodities. This could be enhancing trade relationship with major producing countries, as we've said earlier. But effectively, as we see more and more of those interventions happening, effectively that should weigh onto the quantification of the indicators that we use as a reduction of risk proportionally. And effectively, ideally, we're flagging those which are at risk now, and maybe in 20 years or in 10 years, hopefully we will see some of those elements slightly going down. Whether they will be delisted as critical is another question. What's the impact in terms of continuous funding and support for the industry if this is achieved through domestic supply is also something that's needed to talk about. But those are question and balance for the future for the government and future policies.
Yeah, I think a good example for that is actually fluorine or the mineral fluorspar, which is used to produce sort of hydrofluoric acid and so on. So at the moment, it plots well to the left in terms of its economic vulnerability for the UK, because under the 5 years we've analysed, the UK was a strong producer. Now, last year that stopped. So if we were to use our current position in fluorspar, which is zero production and therefore 100% net import reliant, that would change the economic vulnerability across to 5, and it would plot above the criticality threshold. So I think if we think about that in reverse and say, well, actually, if we reinstated fluorspar mining just as a hypothetical example, then yeah, it would shift to the left. So, and that's a good thing because we would be achieving that sort of resilience of supply, that security of supply to support the UK industries and the various environmental, social, and economic goals that we have.
Next question. I think for yourself, Gavin, has there been any recalculation of the criticality since the workshop at the end of September? If so, why, and what has changed?
We've always gone through a very rigorous QA, QC process. And so certainly as that's evolved, there's certainly been some changes, and that's part of the normal process in science. You build your data sets, you do your quality control checks, and certainly there's been some changes between as the process has evolved. So certainly.
Question I can actually answer here, and that is how can we access the recording of the meeting? So the recording we'll do some captions, so it's accessible, and that will be made available next week through the website. I think there's an event page on the BGS website with all the details. We'll put a YouTube link on there, and we'll also link to it from the CMIC website as well. Okay, a question for yourself, Pierre. Substitution has not been mentioned very much. What potential does the team feel for material substitution to alleviate the criticality of elements, or indeed substitution of the products that incorporate critical minerals?
Right, so this is something we effectively decided to discount from our assessment this time compared to previous years, because effectively there is a lot of doubt that this indicator actually usually bring forward added value to lowering the risk on the elements that are substituted. Effectively, most of the time, if we are aiming for maintaining the performance of the material that we're using, the component that we're trying to develop, and substituting one element for something which provide similar performance for a similar cost, most of the time we are substituting a critical metals with another critical metals. And effectively, this is also industry dependent, application dependent, and make the assessment of the overall substitutability indicator very complicated. We can take the example of LFP batteries versus NMC type batteries, where effectively this is a successful substitution, but it has definitely drastically reduced criticality in other form, in other indicator. Effectively, the substitution of cobalt to iron by iron and phosphate has effectively reduced the demand for cobalt, and this is picked up in other dynamic indicators. To some extent, this is incorporated in an indirected way, but it's a notion which is very complex to evaluate in such an assessment.
I'd add there as well that there are examples, as we sort of pointed to with cobalt and the DRC in the late 70s, and the aerospace sector substituted. It's not always easy to predict. It's not always easy to actually make happen. All right, and so there's a lot of uncertainty about how successful you could be with substitution. And also we know that if you substitute, you're often doing so with affecting the performance. And so you can't achieve the sort of same quality of product or service that you actually that material is used for in the first place. So I think there's a lot of uncertainty as to how accurate substitution can really help in a criticality assessment, which is why we've chosen to not include it this time.
The next question is a follow-up to a question that was answered earlier, and that was in regards to where we're advising the government that this should be reviewed every 3 to 5 years. The question asks, what's the justification for this when we have spent a long time in the Q&A and the presentation talking about the dynamic nature of the data?
Yeah, it's a great question. There's a lot of work. It's taken us several months to be able to work through all of the data, pull this together, and deliver this project, which is why we think there's a need to be able to do a rapid response. So if we take a particular commodity, there's a supply disruption or of some sort, we can go through and actually do that very, very quickly. So we don't have to wait another 3 years to be able to look at that. But then we're only looking at that particular commodity. that's okay. It's a rapid response. It's not meant to be a full comprehensive criticality assessment. So I think there's a balance there we need to be able to strike between doing a comprehensive assessment of all materials and where the sort of current position is versus being able to do a rapid response. There's a trade issue, or there's been an environmental problem or a social issue, for example, that's impacted supply. And therefore we can go in, update some of the data and see what's changed between, say, if we did this in a year's time for, let's say, there was restrictions around the global flow of tungsten, then we could look at the data, update that, and say how much has changed in some of the indicators, and what does that mean? So how much more critical might tungsten be in that sort of scenario? And so I think that's the sort of, we've got to be able to balance off. So there's a lot of work and going through. There's hundreds and hundreds of trade codes to go through. We've got 82 commodities to sort of pull together the data for. And get all of that sort of synthesized into the spreadsheet so we can do the sort of calculations and pull that together. So I think that's sort of why these full assessments are only done now, roughly every 2 or 3 years, and that's the same in the EU as it is elsewhere. It's the legal mandate in the US as well is for these things to be done every 3 years. But I think there's a role there to be able to say there's an opportunity to develop a methodology that is a more rapid response. And so that way we can go in and analyze a particular commodity, and we can do that much more quickly and efficiently to then provide advice on what are some of the options or the issues there.
Great, thanks, Gavin. Pierre, the next one for yourself. How much have you quantified the potential availability of critical raw materials and legacy waste in the UK? For example, in coal tips, mining waste dumps, PFA, coal-fired power stations, metal refining slags, water treatment, work sludges, and so on.
We haven't been able to do this assessment throughout the whole of the products, obviously, that we evaluated. Some of those have well-defined codes for waste and scraps in the trade data, and effectively it highlights some of the major, I would qualify this as major leakage of material that the UK is producing or is not dealing with, notably for copper or for tungsten. So effectively, tungsten is the 3rd largest world exporter of tungsten in the world, and this is due mostly into various forms. But there is definite potential for valorizing secondary sources as a source of material for extraction effectively. Coal fly ash is a good example, and we're notably touching on this subject very briefly into the report, saying that stopping coal-fired power station in the UK, whilst it's a good thing for reducing our CO2 emission, also therefore reduce the stocks of available coal fly ash from which we could derive some other elements or make use in cement and other lightweight construction material. So there's always a trade-off between everything. As to the mine waste in the UK, the historical mine wastes represent fairly small quantities, small volumes, that would justify really a very strong reinvestigation of some of the old stockpiles. But effectively, there is another issue associated with those historical exploitation areas, that most of them are currently heritage sites or located within areas of natural protection and so on. So effectively, there is this dimension which is part of the history of the UK, and we not really have stockpiled enough of the volume, because this exploitation happened a century ago or more than that sometimes, to really justify the volume an industry would currently look at valorizing.
I think another point to sort of add in there as well is that when you're looking at mine waste, sometimes you can go in and there are certainly many examples, certainly from my research in Australia and other colleagues there as well, where you can go in, a site was processed for gold, and there may be bismuth or tellurium in the tailings there, for example. So there's certain examples where that's possible, but you have to have the data to be able to do that. And there are other sites as well where you may not go in just to clean up a site. If you look in Australia, there's examples where you would go in, if you look at the Mount Lyell and the Mount Morgan mines with gold and copper, you go in and reprocess those tailings with one of the main aims of actually cleaning them up and actually remediating them. Now you reprocess the tailings and you maybe treat the acid mine waters to recover, different elements or critical minerals, for example. And that may be how you justify some of the revenue for the remediation. But sometimes there's other justifications as well. And I think certainly, as Pierre sort of said, a lot of the mining in the UK was a much more historic, much older era, and is much smaller scale. But doesn't mean it's not worth looking at, and it's something that we think is certainly worth looking at in more detail. But at the moment, I think the issue is really are understanding some of the technologies and trade flows. That's sort of where I suppose that opportunity around the secondary trade flows is really important.
Thanks, Dylan. Another one of the rare questions that I can answer. So someone's asking about the next Critical Minerals Conference to be held at Keyworth and where they can get more information. Invites and details are to follow, but if you would like to express an interest, you can simply email the inquiries at BGS mailbox that Gavin mentioned earlier, or there's also the BGS Corporate Comms inbox, which is on your invite, your Zoom invite, and reminder for this conference, and we'll pass your interest onto the team to get further details. Next question for yourself, Pierre. How can deep sea mining play a role in supply chain development and growth?
So deep sea mining is a very delicate subject, quite hotly debated at the moment. Effectively, there's well-characterized mineral resources potential in the oceans. Some of them occurs within the exclusive zone of some countries. Some are within the high seas and therefore fall under the regulation of the United Nations. Sorry. Effectively, deep sea mining, we could make the parallel with space mining for that matter, but deep sea mining is a bit further ahead in terms of potential development, would be a way of diversifying supply chain and creating new centers of production. Effectively, there are some well-known advantage to deep sea mining, but also a lot of hurdles around stewardship, economic repartition between countries, as well as obviously environmental consideration around, well, exploiting this new frontier potentially of mining. There have been obviously some exploitation already happening in some location, notably in the Red Sea, back into the 70s, 80s. So there is already a history of deep sea mining happening. Some nations are actively looking for developing potentially this industry. Others are positioning themselves for a moratorium to wait until we have more information to be able to properly take a decision. So it is an opportunity, and I think the greatest opportunity that we have is effectively properly regulating an industry before it actually starts any activity. So if done right, this could be a good opportunity, but we need to make sure that everybody agrees in this consensus on what defines right, effectively.
Thanks, Pierre. And another one, I think, for yourself, as most of these critical minerals are produced using extractive metallurgy, has the criticality of the reagents required in the extraction be considered alongside the minerals themselves?
Right. That's a very interesting one from a methodology perspective. Effectively, we've assessed all the industrial sectors in which each candidate material contributes. So effectively, if one is used in the processing or the chemical industry, the refining process, it's the contribution of that element to that stage of the industry. But effectively, it's very difficult to evaluate how much one element contributes to the production or refining of another element and whether that contributes to its criticality. This is an interesting point and effectively something eventually to consider for future assessments, see how we can potentially incorporate that, include it, which would effectively demultiply potential criticality.
I think one comment I'd add there as well is we could see some of these issues coming. The reduction, the gradual reduction in fossil fuel use will reduce the availability of sulfur. Now, sulfur is used to make sulfuric acid, which is an input to a huge array of different industries, whether it's chemical or extractive metallurgy and many others. And so in some parts of the world, sulfuric acid is actually a really critical commodity. regardless of whether one calls sulfur a critical mineral or not. It's actually crucial for a lot of industries, and they're always worried about maintaining their secure supply chain. So I think we can see some of these issues coming, but from a methodological point of view, as sort of Pierre was sort of talking through, we allocate to end use, we don't go through the start. And if we're looking at the start of things, we'd have to start factoring in the platinum that's used in petroleum refining and start to go through a huge variety of the processes that are used to produce every material and product that we make. And that level of data is often hard to validate, like the total amounts of chemicals, the total different reagents, all of these things that sort of help to achieve a product by itself, whether it's a phone, a car, or whatever. That would be an enormous task, but it's hopefully that helps.
Okay, we're on to the last couple of questions. So the next one's asking about uranium, which the question highlights as a cornerstone element of the nuclear industry. They would like to know, for what reason did it fail to meet the threshold for criticality, and what factors influenced this outcome?
I'm happy to take lead on that one. If you look at uranium, there's a significant fraction that comes from Kazakhstan, but you also have a significant amount coming from Canada, Australia, and other countries that score reasonably to very highly on things like their ESG ranking. So from a global supply risk point of view, uranium is fairly widely supplied, and therefore its supply risk is lower than other things such as rare earth elements, which are mostly coming from China, or more recently Myanmar, where their ESG scores are obviously much poorer. So when you're looking at the economic vulnerability, it does have a single use, and that attracts to electricity production in the UK. And so when you go through those sorts of numbers, uranium plots where it does. So that's sort of where it's now. That's not to say it won't change in the future. I think there's certainly some dynamics. Australia is no longer as a bigger producer. The Ranger uranium mine is now closed, so we'll see what happens in the uranium space. But that's the reasons why uranium plots where it does.
Thanks, Gavin. Okay, the next question asks about the noble gases and notes that only helium was considered. So, what is there a reason why the other noble gases weren't considered in this assessment?
Happy to take the lead on that one. Helium is almost entirely a byproduct, right? Mostly petroleum refining, and so it's currently extracted as a raw material. Others are actually extracted from our atmosphere, things like argon. So there's no concerns about, I suppose, resource depletion or anything else like that. It basically is produced as effectively as a processed product, really. So from a raw material perspective, helium is worth looking at, and helium has some very particular uses as well, especially in sort of medical technology such as MRIs and so on. So helium is worth including, but we didn't feel that the need to look at things like argon because it's extracted from our atmosphere. So and there's no constraint on that per se.
Thanks, Gavin. We're at past, and I'd like to finish with one of my own questions, if I may. And I'll start with yourself, Pierre, but it's the same question to both of you. Given that a lot of the questions and your presentation himself, you said this is a dynamic, it's always evolving in terms of criticality and needs. What minerals have you got your eye on, or what do you think could be developing or interesting stories over the years ahead, and why?
Well, that is quite a loaded question.
Sorry.
I think effectively there is, having worked on these problematic over the last 3 years now, I'm seeing how rapidly the landscape is evolving. So effectively, there might be a need to rethink the way we do those criticality assessment and build on all the data analysis, the databases, the way we're doing those analyses and trying to improve them so that they can be updated more rapidly. So those are potential projects we're looking into, trying to develop for the next few years. Effectively, how to build up a system into which we can rapidly input, that can be interactive potentially for stakeholders to consult in real time. But because our job is also to provide good quality data onto which people can rely, there is a need to explore really the sensitivity and how responsive we can be when some of the data is very much a lot of noise around different things and we need to see the long-term trends. So there is a lot of work to be done on those cases. As to some of my favorite topics, well, I think batteries obviously are going to be one of the drive for the future. And I really look forward to them.
I see what you did with Drive there as well. Nicely done. And yourself,
Yeah,
Gavin?
I think I'd add, copper is going to be fascinating to see how that evolves in many ways. There are real issues with copper, and that's not that we can't see where those issues are. They're environmental, they're social, they're governance. They're not geological. We know there's plenty of copper out there that could be developed. It's a matter of how we develop them and the terms and conditions, I guess. So copper is certainly one to look at. But I love the whole periodic table. I think they all have each of their individual stories. And there are some elements that are, I suppose, more popular than others, like the lithiums and the rare earths and so on. But we need to understand all of those dynamics around all of them, and some of them can change. And so I think, whether it's tungsten, whether it's lithium, and others, I think there's certainly some really fascinating sort of potential in them in the near future. So I think we look forward to getting stuck into a whole range of those different questions and commodities and technologies. So, but again, if you think of something like quantum computing, it's not just the elements; it's also the high purity nature of them, isotopic purity, all sorts of characteristics we rarely get to look at. So I think that there's some other ways we can look at these sorts of technologies and issues and stuff we need to think about going forward.
I was about to add effectively how will AI develop in the future exponentially, potentially even faster than exponential development at the current rates. How is that going to impact material demand? How is that going to interact and change the way we use different material, potentially the discovery rate of new mineral deposits if we apply AI into exploration, but also how does AI improve the design of the materials that we use currently, and how does that help us reduce potentially some of the material intensity in various applications is a fantastic topic.
Sounds like a great subject for another webinar down the road. Okay, on that note, can I extend my thanks to both you, Gavin and Pierre, for an excellent presentation and answering so many fantastic questions. Also, all the people that took the time to join us for this webinar. We had 300 people join us live, which is fantastic. We've literally got 100 questions, which we'll take our time and respond to and get a recording out. So thank you very much for joining us.
Thank you very much.
Thank you. Been a pleasure.